Here's my first one. Okay. Excuse me, I was afraid that would happen. Okay, good morning. Sorry about the little exchange of computers there. I would also like to thank the organizers for bringing us to this wonderful place in Italy. It's certainly a fantastic location, and I personally have found this workshop to be very inspiring indeed, because as you will learn shortly, some of the concepts and ideas that I myself have been working on are very much in alignment with much of what we've been hearing over the last 3 weeks or however long we've been here. And, and therefore I'm very sympathetic, and I hope you will be very sympathetic to some of the things that I'm trying to propound. I'm a speech technologist, which means that I am primarily interested in creating artificial devices which will mimic the behavior of human spoken language in order that we can construct machines which will solve certain applications, requirements, and give us a technology which will help. Let's get rid of that. We don't need that, do we? Oops. Right, good. A technology which will, in some sense, allow people to interact with automated systems in some efficient way. So for those of you who are not familiar at all with this area of science and technology, I'm basically talking about things like automatic speech recognition. So these are devices that will recognize what you as a person will say, for example, to allow you to use your voice to interact with systems rather than a conventional input medium such as a keyboard. The opposite technology to automatic speech recognition is text-to-speech synthesis. So this is arranging for a machine to generate speech and therefore providing information to a user on a verbal channel, an acoustic channel, rather than, for example, a visual channel. If you put those two technologies together, then you can configure what is commonly known as a spoken language dialogue system. So this is like a conversational interaction between a human being and a machine, for example, to replace everyday interactions like booking travel arrangements and allowing that to be done by voice. So actually this has been quite a successful area of technological development over the last 20 or so years. Most of you sitting here actually own an automatic speech recognizer. You probably don't realize that, but I'm sure you all have a mobile phone, and I'm also sure that your mobile phone contains a voice dialing facility. How many people are aware that their phone has such a facility? Right, and how many people have used it? Yeah. Oh, good, wow, okay. Yeah, that's a predictable result, and that's rather important to what I'm going to come to a little later on. Well, actually, people in the business are usually the worst. You may also be aware that it's possible now, since '97, to have some pretty sophisticated software which will run on your PC, which will allow you to dictate documents or control Windows, for example. And indeed, in just recent months, Windows Vista was announced, and this facility is now embedded in the operating system. You don't have to go out and buy any specialized software. Has anybody used any of this kind of software? Tried it? How many people still use it? Right. Interesting. The biggest market area is in what's called interactive voice response. So this is in replacing interactions over the telephone for fairly simple, mundane operations like paying your gas bill or booking cinema tickets, seems to be particularly popular in the UK. And here you're using recognition and synthesis as a relatively straightforward kind to provide automation. And lots of people now are coming in face-to-face with this kind of technology. And what's behind all this, of course, is the very common phrase that speech is the most natural way that humans and machines would wish to interact. Just to give you a little bit taster of what's going on behind the scenes in something like an interactive voice response system, the basic architecture right now is very straightforward. So you have incoming and outgoing speech on the left. You have an automatic speech recognizer, which produces text, if you like, textual representation that has to be interpreted by a language interpreter. And then what is important, of course, is the right-hand side. You have the application. This is what the person is attempting to do. Because people don't present their inquiries in fully formed, in a full form, there is a need to have a process which manages the interaction, manages the conversation, and is able to interact with the application, and that's commonly referred to as a dialogue manager. Just to look a little more inside automatic speech recognition, so you might start with a speech signal, do some pre-processing, some signal processing, might extract some features which are phonetic features relevant to the signal, segment it phonetically, determine what the phonetic content is, have a lexical access process, some parsing, semantic interpretation using various knowledge sources, a rule base on the phonetic side, a lexicon, of course, a grammar for the syntax area, some sort of high-level knowledge base. That's essentially a bottom-up process. One can also hypothesize top-down processes. And what is special, some people should be getting uncomfortable at this point. What is special about this, of course, is this doesn't work. This is very old idea. This is what was done in the 1970s and was shown to be a completely useless mechanism, functional approach to attempting to build a device that could truly recognize what people say. This is what works. This is a contemporary automatic speech recognizer. There are only two functions. There's the front-end signal processing. Of course, we have to analyze the waveform and present some representation of which contains information in a useful form. And the process of recognition is right now is defined as search. It is a search through a state space of possible explanations of the incoming signal. Now, this sounds incredibly trivial, but it turns out to be a very powerful mechanism indeed for defining recognition and for solving the recognition problem. All the complexity is hidden. The complexity is here. Where do you get the data structure which you search in order to perform recognition? And that data structure is effectively pre-compiled using all the knowledge that I mentioned previously. And I'm not going to have time to go through this, but if you look at all the different components, you can see that what happens is that we now have a kind of top-down process which is generating hypotheses of possible explanations of the input. Everything is cast within a probabilistic framework, so mathematically we know what we're doing, and the definition of recognition is and interpretation indeed, is the most derivation of the most probable explanation of the incoming signal given the priors defined in our various models. That is, if you think about it, a kind of analysis by synthesis approach. And I want you to hold that idea in your mind because we'll be coming back to that. So I thought I'd just play a little bit of, to illustrate the other side, the synthesis side, I thought I'd just play a little bit of contemporary text-to-speech synthesis for you.
Hello everybody. This is an example of contemporary text-to-speech synthesis as provided by the Italian company Lecce. Thanks for including me in a meeting asking whether a neural theory of language is possible. For myself, I'm more interested in whether a computational engineering theory of language is possible. Bye.
So that is absolutely up to the moment. That was downloaded yesterday off of Lecce's site. Lecce, as you heard, is an Italian company doing very well with this kind of technology. But I hope you also detected this was a little strange in places. The emphasis was on the wrong words, and we also had some laughter there, which, of course, it has no idea what it's doing. It was just told to emit those words. Just for your interest...
Prego. By the way, I can also speak in Italian. Unfortunately, Roger doesn't know any. So this is the result. Subvia.
So, interestingly, if you put English into a system designed to speak Italian, it speaks English with an Italian accent, which I thought very nice, very nice. Okay, so what is going on in speech technology right now? Well, we have seen for about the last 20 years steady progress. Year on year, things have been getting better, and it's quite impressive, and this is obviously a very good thing. Those improvements have come from essentially what we call corpus-driven statistical modeling techniques. We're using stochastic modeling of processes, automata theory, things like this. Hidden Markov models, you may have heard about, is a sort of an underlying modeling paradigm. And the parameters of models are estimated from substantial quantities of data. And by this, I mean hundreds and thousands of hours of speech material are used to estimate the parameters of these models. There's also, of course, been a dramatic increase in computer power, and what is particularly interesting in this field is that there is public benchmark testing. Year on year, there is competition. People are challenged to recognize speech more accurately than their competing laboratories, and this has driven performance up year on year, so that's obviously a very good thing. Now, what is interesting, and is probably very obvious to you from what I've said so far, that none of this progress is coming from any great insights into what you and I are doing when we're speaking. It's not coming from the human language technology, human spoken language area at all. Now, that may not be a good thing. That depends on your personal view. A lot of engineering laboratories take the view that that's of no relevance whatsoever, as long as performance is increasing. But there are some real issues. First of all, this kind of technology is actually quite fragile in real conditions. So although it can perform exceptionally well, if the situation is as more of an everyday situation, you're trying to make your theatre booking using your mobile phone in a railway station, you will not succeed. It's also incredibly expensive to move from application to application, precisely because it depends on such massive amounts of training material. Because of these thousands of hours, which are all very specific to one specific application, you have to do that again if you're moving to another language or to another application. That is obviously not a good thing. And another really worrying aspect to what is going on in the technology right now is that performance is actually asymptoting, and it's asymptoting not only well short of what a human being can do in terms of ability to process and recognize language, but it's also falling short of what is actually necessary for a lot of anticipated applications. That is a very bad thing, and we therefore need to change the paradigm. Something has to give in, and this is me speaking now, that's my campaign, that we actually need a paradigm shift in the technology. Although we have some pretty fancy and clever techniques which do remarkable things, we actually need something else if we're to cover this shortfall. Just to give you a feel for the difference, this is a classic study. It's getting a bit old now, but it hasn't really changed. This is a comparison of human and machine speech recognition performance on a range of tasks, from connected digit recognition here through read newspapers to conversational telephone speech, and the error rate, which of course should be low, is plotted in a log scale on the vertical axis, and the consequence of doing that is that you can see pretty much across the board there's an order of magnitude difference or more between human performance and automatic performance. So it's not good enough, and a lot of people have been very high up places within the technology. Oh, right, okay. In Microsoft, for example, and there have been these statements that we have still face some very major challenges. And the other thing is, I threw in this line that it's natural to talk to a machine. It is not natural to talk to a machine. Well, maybe for some people there, but I certainly do not find it natural to talk to a machine. It's natural to talk to people. And there is this wonderful illustration. This is called Blind Date. This guy is on a blind date with this girl, and I'll just play a short section of this to give you the flavor.
Hi, I'm Julie.
Nice to
Finally meet you. I haven't been on a blind date in a while. So, Doug told me you work in customer service.
That's right. I do the voice recordings for companies such as United Airlines, Blue Cross, and Amtrak.
Wow, Amtrak, huh? Well, then I guess I have talked to you before.
I'm sorry, I didn't get that.
Oh. No, nothing. Stupid joke.
Hey, can I get you something to drink?
What do you think, Julia? Latte or cappuccino or something?
Did you say latte or cappuccino?
I said both. You know, do you want a latte or cappuccino?
My mistake. Cappuccino would be great. Gary, before we go any further, let me get some information.
Sure.
Please say your age.
Oh, yeah. I get that a lot. I know I look young, but I'm actually 29.
I think you said 19. Did I get that right?
No, 29.
I think you said 9. Did I get that right?
No. Wow, 29.
Okay, got it.
Okay, I'll stop that there, but there is more of that, and it's just a spectacular illustration of the awful reality that actually people are now faced with these automated applications. There is a huge mismatch between humans' ability to interact and the machine's ability to interact right now. So let's listen to a little bit of real human speech interaction. In fact, we've interestingly, over the last couple of days, we've hardly heard any speech, and we certainly haven't heard any what I call everyday speech. So this, if you just tune yourself now to a Yorkshire accent in Britain, these are recordings from Sheffield. Let's just listen to some everyday interaction.
You speak normal English with a slight Sheffield accent, and you speak dialect. If you were annoyed, would you go into dialect or would you stay in straight English?
I go into dialect. I go into dialect.
Why?
Oh, I don't know. It's just something in me. Just
When I get angry, I just go, why is man and man getting me angry?
He will stay in Sheffield and get mad, but I revert. I don't know why. I just use my dialect because I don't know. It's like when my parents. It's probably got it from my parents because when they got mad, they flipped into their dialect as well. So it's probably I just took it from them. But I prefer it. I prefer it for some reason. That's me why.
Is it something about the way are you able to express yourself better?
Yeah. Less words, but they get to the point quick.
Okay, let's. So that was just normal everyday conversation, and hopefully you were able to follow that, even though for many of you it's non-native. Let's just listen to a few snippets now.
With a slight Sheffield accent.
So that you probably noticed that she had a problem with her production and went back and restarted that word. Now that is a major problem for the technology, but it's absolutely no problem at all for a human listener. Now we've got not only overlapping behavior, but it was coming out of people's mouths. This is not speech. It's certainly related to the communication. It flowed beautifully with everything else, and it has significant communicative information. But where does that sit in our spectrum of behaviors?
Why?
And here's a very straightforward word, which you can look up the pronunciation in a pronouncing dictionary and stick that into your automatic speech recognizer. You will never find that beautifully phrased pronunciation, which is therefore, again, strong communicative reasons in context of the dialogue.
But I revert.
I don't know whether you noticed that at all. I mean, he's maintaining his place. He's, all kinds of planning activities are going on, and there is evidence. People like Herb Clark study this kind of stuff, and this kind of behavior is, in some sense, purposeful. You are, listeners understand what is going on here. You have no trouble in understanding that this person is still planning what they're about to say, and but they're maintaining their hold on their position.
I don't know. It's like when my parents. It's probably got it from my parents.
So we have some repeats.
But I prefer it. I prefer it for some reason. Yeah. Less words.
Or, to put it another way, more words. So, what inspiration can we draw from the kinds of research that's going on in human spoken language, which we have representatives here? One of the things that a technologist very quickly discovers is that there's just the most enormous amount of information, and it's very diverse, and it involves many different disciplines. In fact, as we were discussing in the bus or at the meal in the last couple of days, it's hard to believe that actually spoken language is actually one behavior because there are so many different people studying it from so many different angles. A lot of knowledge in this area is based on indirect observation. In other words, you don't have access to the inner workings. You're trying to deduce what is going on. And as a consequence, it's not surprising, therefore, there's an awful lot known about the peripheral activity, about articulation, about auditory system, and rather less is known the further up you go in the chain. And because of the fragmentation, what one sees as a technologist, of course, is a number of different models which cope with or model small aspects of behavior, but the biggest issue for people like me is that none of these things are even intended to work together. There is no integration, no overall overarching theory, and a lot of these models are descriptive rather than computational anyway. So how would one implement such a thing within a computer framework? So there's quite a buzz in the air right now, and one of the challenges that is facing the speech science and speech technology communities is to bridge the gap, and the funding agencies are getting behind this. We need to bridge the gap. But it's actually really difficult to do this. It's very difficult to exploit knowledge, as you might say, about human spoken language. But there have been attempts. So, here I just cite a few here. I'm not going to explain them in any detail, but there have been attempts. But what is sort of universally true about all such attempts is that they all work worse. And remember, we're in a regime where we can test how well these things work. They all work worse than a mainstream system. And that is a seriously bad piece of news. So what is the way forward? Well, having done some thinking about this and having had the luxury of being able to look around at different, being inspired by different ideas, it is certainly come to, I have certainly come to the conclusion that we, within technology and indeed in speech processing in general, probably need to start looking way outside our own areas into areas like cognition and the behavior of living systems, rather than sticking strictly within our spoken language domain, which means that unfortunately, we're going to have to grapple with some pretty big issues, many of which are being discussed here, which is why it's so exciting to be at this meeting, such as intelligence, consciousness, thought, emotion, very hot topic in speech right now, but being treated very superficially indeed, and indeed the structure and functioning of the brain. So what kinds of insights can one derive? So this is my sort of personal view of some things that I have seen looking around, which have stimulated me and which I can relate to potential computational solutions and therefore to a future technology. And here are some of the topics that I'm going to absolutely race through right now. So the illusion of invariance. Invariance is a really, this went sort of almost a taboo word. It's a really dangerous word in speech technology circles because, of course, when you're faced with the reality of the signal, when you see real signals in real-world environments, the notion of invariance can only be interpreted as having a very high-level aspect. There is very little evidence for nuggets of stability, in cognitive stability in the signal itself. We need to go beyond that. And this is not just true of speech. This is true of human behavior, or not just human behavior, but this is true of the behavior of living organisms in general. Living organisms are incredibly variable in their behavior. And this classic sort of Brunswickian view of stimulus-response relationships, of course, has held sway for a very long time. But there is an alternative to stimulus response, and that, for me, is typified by some work by a guy called Powers, who wrote a book in 1973 called Behaviour, the Control of Perception. Now, I think Art was touching on this yesterday, the idea that actually this invariance is a complete illusion and that the perceptual process is not driving behavior, as in a stimulus-response model, but it is behavior, the need to act, and why it is that an organism would need to act in any way whatsoever, that is driving the perceptual process, and indeed determining whether the behavior and the actions of an organism suit its internal needs. So we're hearing a lot about control theory, and this leads to what is called perceptual control theory, which Powers published in his book. And a control feedback process, of course, is a very powerful way for maintaining behavior in the face of disturbance. That is the importance of all this. It's an ability to accommodate unpredictable circumstances. Rather than computing analytic solutions to problems, a control feedback process gives you the ability to solve problems in the face of unknowns. So here we have a classic control feedback process cast in these terms. So the reference signal would be viewed as the intention of the organism. The realization of that intention is some motor behavior. Now, in the environment, there may be some disturbance, a bite block, loud noises, people in your way, it could be anything at all, but which disturbs the realization. And your sensors determine the consequences of the action, and of course you go around, you interpret the consequences, compare that with the intention, and around the loop you go. The analogy I like to give is, of course, keeping a room at a certain temperature. The classic room, if you're not familiar with control feedback processes, imagine how you keep a room at a constant temperature. If you're a stochastic modeling person, straight out of our community, you might say, right, we need a massive database, we need thousands of hours of recordings of temperatures in this room, we need to know the air volume, we need to know how many windows, whether they're open or closed, how many people, we need to know everything that's possible to know about that environment. We'll build a massive analytical model which will predict what to do with the heating control to accommodate all these different situations. And then somebody comes along with some change, just opens a window, and your model, it wasn't in your model and you can't cope, which is ridiculous because we all know that you only need a thermostat. And so a control feedback process can accommodate an infinity of possible variation where an analytic solution would be ridiculous. So Powers proposed actually a hierarchical arrangement of control systems, and again, I'm not going to go into this, I'm really just advertising this as a set of ideas, and therefore was able to predict human behavior and behavior in general in a range of different aspects. Now, what is particularly interesting in this, and this again was mentioned by Art yesterday, Rick Grush, for example, one of many, has hypothesized on the basis that control systems and feedback from control systems may be too slow, that you can use a predictor or an emulator to emulate the control process, and therefore you can maintain control over what would otherwise be loop delays which are too long. And so what we have here is an emulation which is mimicking the activity of the controlled system itself. Now, once you are into this framework, you're immediately jumping into the possibility of, immediately jumping into the possibility of what we could call mental imagery, because you now have within this organism an emulator which is not really controlling the outside world, but it is mimicking the outside world, and therefore can be used for all kinds of different purposes, not just predicting your own behavior. We're going to come to that. So this leaps into notions like the chameleon effect, where this is just evidence, if you like, for these kinds of possibility of these imitative emulation processes, which are easily demonstrated. When you have such mental simulations, then we have all kinds of interesting possibilities, including generating expectations and predictions, which was also mentioned yesterday. Now, I'm thinking here not just of a single system, but of course a complex hierarchical arrangement and indeed parallel processes. But the general notion is such an emulation framework can generate predictions. And not only can you predict what you're going to be doing, but you can now recruit this to predict the behavior of another organism. Now, why would you want to predict behavior? Well, predicting the behavior of another organism is incredibly important in survival. You need very fast response times. And having a prediction mechanism has a very strong advantage over a purely reactive arrangement, because not only can you predict, but the power of the predictor, because the way I would view a predictor is as a search process, is that you can come up with globally optimal solutions rather than locally optimal solutions. Which means, for example, that you can derive a strategic approach to predator avoidance by going around something rather than perhaps taking the most direct route. What looks good right now may end up being ultimately the worst thing you could do. So having access to emulation and prediction mechanisms gives rise to these planning possibilities, and planning gives rise to things like global and local trading, local optimality for global optimality. Why do I think that's interesting? Because it turns out to be exactly the kinds of mechanisms that are used in current automatic speech recognition devices. We exploit this notion of search through state spaces to find globally optimal solutions precisely to do things like automatic speech recognition. Now, in order to do that, then the emulator is effectively acting as a forward model of the prey. Now, another nice area which I don't have time to cover in any depth, I'm sure many of you are aware of this book by Jeff Hawkins. Jeff Hawkins is actually the CEO of Palm Computing, but in his private life, he's a neuroscientist, I understand. And he has written this rather nice book where he introduces something called the memory prediction framework. And essentially, a lot of the ideas that he's promoting in there can be cast within many of the things that I've just been saying. So we'll jump straight on from that. Now, one of the things that about learning models, and we also heard this from Art yesterday, is that it can take a long time to learn a forward model. If I'm attempting to build a model of another organism, I can either build it from scratch, or I could actually recruit a model of myself, which I have hopefully a rather better understanding, and I can recruit that to model others. And so this notion of copy of self appears to be supported within a lot of research that people like yourselves and others are currently doing. And this allows now the ability to not only, by modeling, projecting self onto others, because oneself has needs, desires, and intentions, you can now interpret the behavior of others with respect to their needs, desires, intentions, as estimated based on your own. And that, of course, is the direct link into theory of mind. So I'm going to jump straight past emotion and head for sensorimotor overlap. So what this is all leading to, and so hopefully what you're seeing here is that I'm really not starting from something like mirror neurons and saying, so what for the technology? I'm kind of constructing a logical argument which leads to, and therefore there must be a value in having something like a mirror neuron structure. So an organism which understands the sense behavior in another by referencing predictions from its own motor behavior, in other words, its own ability to perform in the world, and which controls its motor behavior by predicting and sensing its effect on the environment. That inevitably means there is sensory-motor connections, perception and production need to be intimately linked, and of course a possible supporting mechanism in the brain is indeed mirror structures. So what's all this got to do with speech? Because I've obviously spun way off into the hinterlands of speech, but just some evidence that some of these control effects are very real. We've heard about hearing impaired individuals. Also, if you delay speech into somebody's ears, it causes serious problems with production. And of course, there's the well-known Lombard effect, whereby individuals vary their pronunciation as a function of the environment in which they find themselves. This is a very old result. If you've not heard such a thing before, let me just play you an example. So this is somebody, it's actually Professor Martin Cook in our lab, if you know Sheffield, who is speaking normally.
The use of auditory masking to produce a reflexive vocal response was introduced in 1911 by Lombard.
And now he puts on some headphones and we feed sort of general pub noise into his ears, and then we ask him to do the same thing again.
The use of auditory masking to produce a reflexive vocal response was introduced in 1911 by Lombard.
Yeah, sorry that was so loud, but part of the point is he not only raised his voice, but he also, you could tell there was some reorganization going on, and even his accent seemed to change slightly. One of the other areas which is very well known to the speech people in terms of reorganization and in particular managing articulatory effort against clarity, given that, given that there is in a living organism, there is a constant tension between the cost of performing a behavior and the effectiveness of performing that behavior for whatever need you have in mind. And this is mapped down into the what's called the H&H theory by Lindblom in terms of speech production. In other words, it is possible to speak at a very high level of clarity, as I'm attempting to do now, but I'm putting in a huge amount of effort, and that's going to mean I need a bigger lunch than you guys because of all that. On the other hand, when you're talking to your family, you're at the other end of the scale. The context is such that they know very much what you're talking about, and therefore is a tendency to be at the hypo end. Another area which is a strong, gives a very strong example of compensatory behavior for serious purposes is in parentese, the way in which caregivers actually speak very differently to children than they speak to adults. And I've got a nice example of that. So here is a mother speaking to another mother about a sheep.
Well, what about sheep?
Well, she really liked that sheep's ear. That I think fit into her mouth very well when she was playing with it. And I thought she was gagging herself for a minute there,
And now let's hear her talking to a child about the sheep.
Let's do the sheep. Let's do the sheep. Look at that. Yes. That little sheep has pink hooves and pink eyelids and a pink nose.
So this is very different, and it's much studied, and I believe explainable. Okay, so what we need to do for modeling spoken language. What this all tells us is that it's time to give up the notion that spoken language is some kind of peripheral activity that's grafted on. It is actually a fundamental part, an intimate part of cognition, which means that something like speech recognition, speech synthesis, and dialogue systems, it's time to stop modeling them independently, because right now in the technological area, these are very different communities. People who work on speech recognition do not talk to people who work on speech synthesis, and they do not talk to the people who work on dialogue systems. And it's time to bring all this together based on the arguments we've seen so far. And what we need to see is a model whereby the talker has in mind the needs of the listeners, and the listener have in mind the intentions of the talkers, which means we need to get rid of this diagram that we saw earlier. Thank you, Joe. This one-way idea, and move more to what Jean-Luc was talking about, which is not a one-way process, but a duplex, the communicative loop between, in this case, human and machines, but where we need to take into account the fact that we not only have potentially one set of control systems operating, but two sets which are loosely connected in some sense with each other for some joint purpose. That's really what I'm trying to get at here. So I'm going to skip over presence, which is not a problem because you can, if you're interested, you can look this up. But what I am proposing is a computational architecture to characterize some of these things. And what is very different about this than mainstream speech technological architectures is that it does indeed try to bring together these different aspects within a single framework. And what is interesting about it is that it has to start, rather than starting with a bottom-up analysis of the signal and asking what is the speech recognition problem, it starts at the very top and says, what is the purpose of these organisms, particularly a human being and a machine? What is the purpose of their interaction, and how is each going to solve its needs? And this puts great pressure on the system to understand the needs of the user, which as potential users of such systems, I'm sure you would fully appreciate. And this is exactly what is wrong with current systems. They have no idea what they're doing or why they're doing it. So let me just point to the fact that there is an architecture here, where I will skip straight through and head for the conclusions. I would like to just dwell for a few seconds on this slide, because some of the key research issues that emerge from this are, I think, rather important. And I've identified 3 areas of behavior within such a sort of loosely interlocked control frameworks. One is communications and entropy management. In other words, an organism needs, and if it's to cooperate to solve its needs and desires, then it has to manage information. And I mean from an information theoretic point of view. It has to organize its behavior in some efficient way to maximize use of the channel in order to exploit the communication channels that it has. And one of the things that language seems to have done is discovered a fantastic mechanism, which is the particulate structure, which allows the combinatorics of language to address a vast array of internal representations from a relatively low-dimensional process here. Management of energy for a living organism is absolutely key. Managing time for a living organism also, if you are to avoid predation and interact and get things done in a timely manner. I realize I'm following the trend of the conference. I'm really going to finish very, very soon. So I just want to finish with just implications for the technology, because what this does imply is a totally new method for speech generation whereby the speech synthesis process has within it a model of the listener, which effectively means this is synthesis by recognition. And a model of recognition which has within it a model of the speaker, which is, if you like, recognition by synthesis. And there are no systems that do this. And what I would just want to say is that once you start embedding one system within the other, you then enter an area of recursive behavior, which is, I think, different to the other kinds of recursion we've been hearing about, but it's a very interesting notion of sharing structures, sharing parameters, which means the learnability of the system is high, but the capabilities are simultaneously very, very high. So you'll be pleased to see this. What I've really tried to do is race through a number of different things and introduce to the notion of this architecture, where I've tried to pull all these ideas together, including many of the things we've been hearing about this week. The architecture is called Presence. If you want to find out more, there are a couple of papers out there which you can find, or on my website, and that's where I finish.
Thank you for listening to Roger's talk. Do you have any questions?
Thanks. Are there questions?
Thank you very much for an excellent talk. It's very fascinating what computer systems now can do, and also it's equally interesting what perspectives they have and what needs obviously doing. I was very glad to see a brain at the end of your talk,
right.
And likewise for the other talks this morning, there wasn't too much brain in them. And then it's sometimes a bit worrying if out of the blue there's suddenly a result on gamma band responses without any theoretical foundation of why there should be a certain process being reflected in a certain specific brain response. So maybe there's still a big gap between. And I just want to point to one thing which is, I think, common to all the presentations this morning. There were terms such as regulation, control, target value, and the whole cybernetic, I would say, metaphor applied to the brain. It is really a metaphor. We do not know what kind of circuits in the brain do these realize these technically very useful mechanisms, and there have been proposals at that end. But I think many of the technical models that now are on their way to being linked to brains are of the kind that, okay, and this model, this control module should actually sit in prefrontal cortex. It should include a few mirror neurons, and that's it. Which is not, I should posit, a mechanistic explanation, as we would hope it might be developed at one stage. Do you have a little comment in this direction?
Only that my interest is in drawing inspiration from those areas to understand the constraints that appear to be operating on the human system, and I wish to utilize whatever information I can get to create a technology which can mimic some of that functionality. If such a model exhibits behavior which is interesting in its own right and can feed back to the other community, then I would see that as a fantastic bonus. But it is probably not what the technologists would see as the main aim of their desired research. I personally, I would like to go further personally, but I wouldn't be so brave as to offer solutions at this very, very early stage. That would be... No, well, exactly. That's why I'm saying helping the technology right now is foremost in my thoughts.
Or let me give a very simple example of such looking at the brain and then coming back to technology. We had a EU project together with the larger community, including colleagues in Parma, and also robotics specialists, and we implemented that action word model in a robot there. And there was a UK competition finally in 2005, I think, where the robots had to perform a very simple task, get a verbal instruction, and then get an object from a table, and then come back and deliver it. And we won with that robot. And it was simply because the light environment and the noise environment was such that the the AI systems failed, and our little, relatively stupid, admittedly stupid mirrorbot succeeded.
Well, that's very encouraging.
It was just an implementation of the action word model I showed yesterday.
I mean, what you're putting your finger on there is fragility in technological solutions, and I think I'm going to give an even stronger response to your previous question now, which is that I think that actually a lot of the main successes in machine learning in general have been driven by the speech community, the speech technology community. Some of the algorithms that we know and love for estimating parameters of complex models and stochastic modeling and search processes. All of these things have found their way out into other communities, and I think it does provide a very sophisticated view of some of the core computational components, which I think could contribute to our understanding of just how some of these neural mechanisms might actually be functioning. But I have no idea what that might be, but I would offer that as we have some very sophisticated processes already within spoken language technology, which I'm not arguing should be thrown away, but should be themselves embedded in a much richer interactive framework.
I think we are forced to move to the next speaker. Thank you very much again.